This week, we're continuing a short series on advanced functions. So I'm going to remind you again, if you haven't already, to watch our first video on the basics of functions here. Last week, we focused on quadratics and polynomials as we learned some new problem types. And this week, we will dive instead into exponentials and rationals. This might remind us of the problems we had last week, except now, instead of a graph, we have a data table. The process is going to be pretty similar, except now we just need to plug in numbers from the table. To be wise about it, let's start with x and y-intercepts. First, we can plug in the y-intercept we see in the table, which is g of 0 equals -1. Evaluating g of 0 in our answer choices is easy. Just remember that anything to the power of 0 is 1. Evaluating each of these, we can find the y-intercepts of all of our functions in our answer choices. Matching with that we found from our table, we can then eliminate both a and c because they don't match. So that leaves us just with b and d. Now, we will take another point from the table, the x-intercept, g of 1 equals 0, compare that again with our functions in the same way. So let's evaluate g of 1 for both. Evaluating, we get g of 1 is 0 for b, and then 1 for d. Now, we want it to be equal to 0, because that's what we have in our table, so we can eliminate d and say that b is the correct answer. It's important to be familiar with exponential functions for these problem types and others. So I'm going to show you the graph of the function we had in our answer seen here. You should identify some key features and recognize the form of exponentials like this. One of them being end behavior, which we'll dive into in our next problem. For example, the end behavior in this graph is to the left as x approaches -infinity, it approaches -2 as you can see there, and as x approaches positive infinity to the right, the function goes towards infinity. Now we see another example similar to the type we've seen before, matching a graph to its function. Last time we tried using x and y-intercepts to solve this type of problem, but that's not really going to work here. Instead, we'll make use of end behavior. What is end behavior? End behavior describes where the function goes as x approaches positive or negative infinity. And there are three statements we can make about end behavior. Either it will approach positive infinity, negative infinity, or some constant number. So the three options we see here, we say as x approaches negative or positive infinity, then the function f of x approaches either, like I said, positive infinity, negative infinity, or a constant number. To see an example of this, we see a function here, which happens to be an exponential, and we would say that as x approaches positive infinity, so to the right, f of x, the value of the function, approaches positive infinity, as we see it going up. To the left, as x approaches negative infinity, we see that it just gets closer and closer to 0, so we say that f of x approaches 0. Now we can use end behavior as a key feature to match our graph with our functions. So we found before that for our graph, as x approaches negative infinity to the left, f of x approaches positive infinity. So we're going to match that with the end behaviors of the functions in the answer choices. So how do we test end behavior from a function? We can't plug in infinity, right? But to get a sense for it, we can just choose a big number and see where it goes approximately. So in this case, to test negative infinity, let's plug in x equals -1000, a pretty big number. So we evaluate f of -1000 for each of these answer choices, and simplifying, for a, we get 2 to the 1000. That's a very, very large number, so we can say that it just goes to infinity, positive infinity, which is what we wanted from our graph. So far, a matches. For b, we evaluate and we have 1 over 2 to the 1000. So 1 over a very large number is approximately 0. So we say that for b, as x approaches negative infinity, f of x approaches 0. That is not the same end behavior from our graph, so we eliminate b based on its end behavior only. For c, we likewise evaluate. We get -1 over 1000, a very small number, and so we say it approaches 0. Likewise for d, we get positive 1 over 1000, still very small, and so it approaches 0 likewise. So for b, c, and d, we can eliminate all of them just based on end behavior. And based on that, we know a has to be the right answer without knowing anything else about this function or the graph. Okay, on to our last example for this video. Again, we're matching a graph with its functions. So what do we recognize from this graph? Well, you should recognize the strange form, the shape it takes, as that of a rational function. You can look at this strange mirrored boomerang shape, which is something that you only see for rational functions. In particular, focus on the middle point, where on one side it goes to positive infinity, and the other side it goes to negative infinity very quickly. That is what we call an asymptote. And that only happens when we have something like 1 over 0 and things blow up. That is something we only see in a rational function. Having recognized the graph as that of a rational function, we can quickly eliminate answer choices C and D, neither of which are rational functions. Now, how do we choose between A and B? There are many options, but why don't we choose the y-intercept? So looking quickly at our graph, we can estimate our y-intercept is somewhere beneath 2. Now we can compare that with our functions. If we look for the y-intercept of the function in A, we would plug in x equals 0, and we get 1 over 0, so things blow up. Remember, that is where we find the asymptote. But comparing with our graph, we have no asymptote at 0, it's instead at x equals 3, like we saw in that line there. So we can eliminate A, and B is the only remaining answer, and that will be correct. Okay, notice how for that last problem, we use y-intercepts as well as recognizing the rational form to get to the answer. So keep in mind that whatever function type you're looking at, whether it be quadratic, polynomial, exponential, or radical, you can use almost any of these strategies to get to an answer. X-intercepts, y-intercepts, and behavior, and much more. Mix and match as you please. In the last 2 videos, we familiarized ourselves with 4 new types of advanced functions: quadratics, polynomials, exponentials, and rationals, as well as some applications to the problems we should expect to see on the SAT. Next week, we will wrap up by learning how to apply function transformations to these types of functions and more.
Hope you liked the video. If you want to hear more and see what else we're up to, hit like and subscribe, and see a new video coming out from Point Avenue every week. If you want to talk to us, hear more about what we're doing, or have any questions, email us at contact@pointavenue.com. Bye!